Assalamu alaikum, everyone. I hope you're doing well. So today we are solving ATP questions from 2019. And this is a paper that I've made by selecting different questions for both IGCSE and O levels. So I'm hoping that this will really help you out in solving the questions for this year, 2019. All right. A chemist heated solid zinc chloride until it became molten. Okay, so we know that solid zinc chloride is an ionic compound, must have heated it to a high temperature. The apparatus shown was then used to pass electricity through the molten zinc chloride. So that is our electrolyte here, molten zinc chloride, using inert electrode. That's important because now this means electrodes will not take part in the reaction. A silver colored solid was formed at the negative electrode. All right. Name the process of breaking down a substance using electricity. That's electrolysis. We know that. Okay. A Bunsen burner was used to heat the zinc chloride. Describe how a Bunsen burner is adjusted to give a very hot flame. Now, this is more important for IGCSE people. You need to know that Bunsen burner has basically a hole on the side. So that hole, if it is open, it gives us more oxygen. So there's going to be a very hot flame. If you close that hole, there's limited oxygen, which means there is not that hot a flame. We call this collar as well. So we need to have an open air hole for this flame. Suggest and explain the expected observation at the positive electrode. They've already told us that you're getting silvery substance on the negative electrode. Now let me see. This is zinc chloride. So I have zinc ions and chloride ions, and those are the only two ions that are here. So zinc will obviously give me zinc, and chloride will give me chlorine. How does it do that? Zinc takes 2 electrons, chloride loses 2 electrons. And that's how I'm getting zinc and chlorine. So because chlorine is a gas and this is high temperature, I will expect bubbles to be seen. And not just that, this is chlorine. We know the color of chlorine, it's a yellow-green gas or just green. So we will see bubbles of green gas. Now that is my observation that I've suggested, but I haven't explained it. My explanation would be, number one, I have to explain why bubbles and why green. So I'll say of chlorine gas. By naming chlorine, I've told why it is green, and by naming the gas, the state, I've told why we are getting bubbles. So that's why iron electrodes cannot be used in this experiment. We already know that iron is more reactive than zinc. In fact, iron is less reactive than zinc, but not just that. Iron is an active electrode. It will react. It's a very reactive metal. So we'll say that iron will react. Okay. So that is an important thing to remember. Okay. Moving on. What difference would the chemist observe at the negative electrode if aqueous zinc chloride were used? So we're using aqueous zinc chloride, which means you are not just getting zinc ions and chloride ions, you're now also getting hydrogen ions and hydroxide ions. And what difference would this make rather than using molten zinc chloride? So first of all, instead of getting zinc, we'll get hydrogen because hydrogen is below zinc in the reactivity series. It's lower in the reactivity series. So the difference is that we will see bubbles on negative electrode on cathode. And the explanation is that hydrogen gas is produced as it is lower in reactivity series. You can also say lower than zinc in the reactivity series. In fact, even if you don't give this reason, like you just say hydrogen gas, that also suffices for this question. When electricity is used to break down concentrated aqueous zinc chlorides, chlorine is produced. Describe a test for chlorine. Now we know that chlorine is an acidic gas, and not just that, it is also bleaching agent. So we can take a litmus paper, and it's better to use a blue litmus paper so we see it going red, but it doesn't matter because it's going to bleach anyway. So we take litmus paper and it is bleached. Okay. The bottle of zinc chloride is labeled corrosive. State one safety precaution that should be taken when using zinc chloride. So this is corrosive, which means you need to make sure that it doesn't touch your skin or your eyes. So that means you should wear gloves and goggles for your eyes. All right. Calcium carbonate reacts with dilute hydrochloric acid. Okay, we have this. This is an interesting reaction because if you notice the states, so notice the states every time you look at these reactions. Overhead, visible changes will be seen in the solid part and in the gaseous part. Why? Because the solid will dissolve and the gas will evaporate. You will see bubbles of that. And it's vigorous bubbling, which means the reaction is really fast. A student investigates the rate of this reaction using 3 samples of calcium carbonate. Each sample has a different particle size. So that is the factor that they're going to use for rate of reaction. So this is a rate of reaction chapter, and they want to do different particle size. That means it quickly tells me that I'm going to get differently sized particles, maybe a powder, maybe some granules. And secondly, because it's rate of reaction, I need to make sure that I have some way of measuring the time. Now, the diagram tells me that you're using a balance, which means it is the mass that is the other thing. But because I want to know the effect of particle size, not the mass, which means I need to make sure mass is same every time this reaction is done. Okay, in each experiment, the student adds all the calcium carbonate in excess, which means calcium carbonate is in excess. It's the HCl which is going to determine how fast, how much of the reaction happens. So that means I need to make sure that HCl is of the same concentration. To dilute HCl in apparatus E. Apparatus E, that is conical flask. We know conical flask is used for mixing, and this one is conical flask. That's my next question here. So it's a conical flask. The weighted bottle is replaced on the balance. The student records the mass every 30 seconds. Okay. You have cotton over there, so it's loosely fitting because we want any bubbles to be made to escape. So they'll pass through, but any air from outside will not permeate into the conical flask. Okay. Which variable other than mass is measured in the experiment? So in this experiment, what are we measuring? We are measuring time because we have mass on one side. And of course, the other thing should be time, right? So time, and I measured using stopwatch. Why does the mass decrease? It decreases because every time there is a reaction in which a gas is produced, mass would decrease. So carbon dioxide escapes or goes out or evaporates. Better word would be escapes. Okay. The student does 2 more experiments. In each experiment, the student uses calcium carbonate of different size. In experiment 2, the student uses small lumps. And in experiment 3, they use powdered calcium carbonate. Okay. So there's 2 variables that the student keeps constant. So the particle size of calcium carbonate is the only variable. So first of all, you're reacting HCl. So you need to make sure the concentration of acid or concentration of HCl remains the same. And secondly, we need to make sure that there's pressure does not affect this reaction because there's no gas in the reactant side. Sure, it is in the product side, but that doesn't matter. Temperature is the second factor that we usually look at. So temperature should be the same because we don't want temperature to affect this reaction. We don't need a catalyst, but even if we had a catalyst, we should make sure it's used in all of them or none of them. Okay, the student plots a graph of the results. Okay, so the fastest one is the one that becomes horizontal first. So I can clearly see that the first one to become horizontal is this one. So that's my experiment with the powder. Yeah, that's experiment 3. Then what did I have in the first one? Large lumps. Okay, so large lumps mean it's going to be the slowest one. So this is the slowest and this is the fastest. Okay, that's easy. Describe how the graphs are used to decide which experiment has the fastest rate. We just told you that the graph becomes horizontal or graph becomes flat. That's how you know that the value is not changing. Write a number in each box. We did that. State how the graph shows that reaction stop. Because the value that is on the mass is not changing anymore. Okay. So how does it tells me that how the graph shows that oh, wait a minute. This shows that graph that the reaction stops, but not the rate. Interesting. So let's see, describe how the graphs are used to decide. So obviously I'll look at the gradient. So fastest rate is the one, the graph with greatest or highest gradient is fastest. Why do the reactions stop? Because the limiting reactant is used up. And in this reaction, limiting reactant was HCl, because notice that they said the student adds calcium carbonate and excess. So that tells me it is the acid that is the limiting reactant, and that is all used up. So all of HCl is used up. When you're writing HCl, make sure that you write small letter for L. It should be distinguishable from capital I, or don't write this, because this might be HCI. Somebody can think of it as HCI. So try to get some way of making sure that it looks small letter. Okay, two substances, solid U and liquid P, were analyzed. Solid U was chromium-3 nitrate. I have chromium-3 and I have nitrate. Tests were done on solid U and liquid V. Complete the expected observations. Okay, so solid U is chromium-3 nitrate. What color would it be? Chromium-3. We already know chromium-3 is green, right? So this should be green, yeah. Solution U. So what did we do? We took solid U, added it to distilled water, and stirred it, obviously, to make sure, shaken to dissolve. So we made sure that it's a solution. It's completely dissolved, and now that is solution U. It is chromium-3 nitrate solution. A few drops of aqueous sodium hydroxide were added to the first portion of solution U. Now I know that chromium-3 nitrate has chromium-3, right? And sodium hydroxide with chromium-3 will give me green precipitate, right? So green precipitate. You can write PPT or the whole precipitate word. And excess were added to the mixture. Now I know that this one, sodium hydroxide, chromium-3 is the one that dissolves. There's also aluminum, there's also zinc. So aluminum, zinc, and chromium, these are the ones that dissolve. Okay, these are the ones that dissolve in sodium hydroxide. So precipitate dissolves, or precipitate is soluble, something like that. Okay. An excess of aqueous ammonia was added to the second portion. You'll get green precipitate again, right? You can also say, some people also mention gray-green precipitate, but just green precipitate is also fine. Aluminum foil and aqueous sodium hydroxide were added. Why do we do that? Because every time you have nitrate, you can test it using this. Aluminum foil is a big hint that you're testing nitrate. Okay, so aluminum foil and all that, and the mixture was heated, the gas produced was tested. So there's going to be gas, they've told us, there's going to be bubbles of that. There's another word for that would be effervescence. Okay, and what's the test for that gas? This is ammonia. So that ammonia gas will obviously dissolve. That ammonia gas will give us turn the red litmus blue because it's basic. So effervescence or bubbles of gas that turns red litmus blue. One of the tests done on liquid V and the observation made are shown. A light spin was used to touch about 1 cm cube of liquid V. Okay. Liquid V set on fire and burned with a smoky blue flame. Now, this is a test for us to know whether we know what the blue flame is for. Now, you know that draw one conclusion about liquid V. Now, this cannot be any metal because they did not tell us that liquid V was at a high temperature. So this can't be a metal. So don't confuse yourself by thinking, oh, wait a minute, I had blue flame for something, so that should be it. No. This one is burning. This one is a fuel. That's it. So the conclusion is it's a fuel. So don't think too hard. Okay, carbon and copper 2 oxide are both black solids. And this is an interesting question because this is a question that's called investigative questions. Okay, and they're interesting and kind of challenging. So I've included two of them in this paper. Carbon and copper 2 oxide are both black solids. Copper 2 oxide reacts with dilute sulfuric acid. By the way, you're supposed to know the color of both of these. You should know that they are both black. Copper 2 oxide reacts with dilute sulfuric acid to form aqueous solution. Of course, copper 2 oxide is basic and H2SO4 is acidic. So they'll produce copper 2 sulfate and water. And we also know that copper 2 sulfate dissolves in water. In fact, it is used to test water. So carbon does not react with or dissolve in sulfuric acid. Neither carbon nor copper oxide dissolve in water. Carbon does not react with or dissolve in dilute sulfuric acid. Neither carbon nor copper 2 oxide dissolve in water. Okay, a mixture contains carbon and copper 2 oxide only. Plan an experiment to produce a sample of pure carbon. So what do we need? We need to separate pure carbon from a mixture of copper 2 oxide. Now, this is interesting because both of them are insoluble. Both of them are unreactive with water or with each other. But the good thing is that we can still separate copper 2 oxide by dissolving it and reacting it with sulfuric acid. Because if we do that, then we will be able to get copper 2 sulfate out and water out. You may use dilute sulfuric acid, distilled water, any of the apparatus usually found. So there's a big hint for us that you can use sulfuric acid. Because if you use sulfuric acid, you're going to get something that is soluble and carbon, which is insoluble. So then it is just like salt and sand problem for us because you can then filter it out and separate carbon, right? So the big issue that was of separating copper 2 oxide has been dissolved by the big issue of using copper 2 oxide and separating it from carbon has been resolved by using sulfuric acid. Okay, so that's what we'll do. Of course, we will sacrifice copper 2 oxide in this process. Okay, so what should we do? The first thing, obviously, you take that thing and add sulfuric acid to it. Now, before you do that, you just make sure that you know what the stepwise method is. So we always give a stepwise method. So first thing would be that add the mixture to conical flask with acid and stir it. Okay, so that's the first thing we'll do. So add the mixture to acid and stir. Now, because this is copper 2 oxide is a base and it's a solid, you might want to heat it as well if you want to react it faster. But even if you don't, if you just stir it thoroughly, it will react then. And now what do you have? You have copper 2 sulfate, which is soluble. You have carbon, which is insoluble, and you have water. So what do? You have insoluble thing, you have a soluble thing. How do you separate the insoluble thing? Filter. So filter and dry the residue that is carbon. Okay. Now, before you do that, before you dry, one thing you should do is, again, before you dry this thing, you filter and wash with distilled water so that any impurities like copper 2 sulfate, if there is left over, it will then dissolve and go away. Now that you've done that, now you dry the residue, that is carbon. इतनी लाइनें उसने फजूल में दी हुई हैं, we don't need that. This is good enough for us. Of course, One more thing that we can add to this is that the filtrate will be blue. So filtrate is blue solution. How do I know that? Because I know copper 2 ions are blue and copper 2 sulfate is blue of copper 2 sulfate. That's something I know. So I've just mentioned it. So this is just some extra information. We did not need this, except if you look at this one, that observations occurring at each stage. So of course, blue solution is an observation you can't miss. Rate of reaction, this is again an investigation question. So rate of reaction between magnesium and dilute hydrochloric acid can be measured, followed by measuring the volume. So we saw a reaction in which they measured the rate of reaction by using mass and the particle size. Now we're looking at how you can use gas volume to figure this out. Okay, so we want to focus on rate of reaction and volume of hydrogen, which means we need to make sure all the other factors remain the same. And what other factors can those be? Mass of magnesium, concentration of sulfuric acid, volume of sulfuric acid. Okay, all of that needs to be fixed so that we can have a good comparison. And that's what we'll do. So first of all, you have magnesium ribbon, dilute sulfuric acid. We add the ribbon. Okay, so we need a conical flask, magnesium in there. So that is magnesium ribbon. Okay, I'm going to add sulfuric acid from the top. I could use a thistle funnel. I could use any other funnel. I could just say that add HCl. I don't want to draw that. It's up to me what I do. I could use a tap funnel as well. So it's totally my choice what I do. So I'm going to use a tap funnel. So it has a tap and it's a funnel. So of course, it's much easier to pour sulfuric acid in there. So there's going to be, is that sulfuric acid? Sorry, it's dilute HCl. So HCl aqueous. Okay, now this will obviously give off hydrogen gas, which I want to collect. So I'm going to use a gas syringe for it. Now, whenever you're drawing gas syringe, make sure that you put these things on there because this shows that this is a graduated gas syringe. This gas syringe allows me to measure the volume. The gas syringe without these will not be able to measure anything. And most importantly, seal this thing once you draw the diagram because this shows that gas will not escape. All right, so I've drawn a label diagram. Always draw a label diagram. A diagram without label is as good as not drawing it. Okay, and this one is gas syringe, to mention that. Okay, now what happens? First of all, I need to make sure that everything else remains the same, which means mass of magnesium is the same, concentration and volume of HCl is the same every time I do this. So I'll say that add, add a known mass, or just say weigh a fixed amount of magnesium and add to fixed volume of HCl solution or HCl aqueous. Okay, so that's this. Now, obviously, gas syringe will obviously fill with gas. So I've already mentioned that. I know this. So now I need to make sure how long it takes for gas to reach a fixed volume. So measure the time taken to produce a certain. Now, because I do not know how much magnesium and how much acid is there, I cannot predict how much volume it will make. But every time, just make sure that you let it reach a certain value, certain volume of hydrogen gas using stopwatch. Because I need to measure time, so why not mention what to measure it with? Okay, so that's it. Now we have done it once, but we don't know, we need more values to figure out the rate. So repeat using different. Here's the thing. I need to change a factor that will not change the volume of hydrogen made, but it will change the rate of reaction. I cannot change the pressure because these are not gases, but I can change the temperature. With different temperature, the rate will change. Okay, so you repeat using different temperature. Okay, you can also mention but with same mass and same concentration. You can mention that if you want. then you can just write your conclusion that the reactions taking the least time is faster. Okay, so that is that. Okay. A liquid hydrocarbon is burned using apparatus shown. The gases produced by burning hydrocarbon move along the delivery tubes and through the boiling point. Okay, so there's liquid hydrocarbons going to produce carbon dioxide and steam, which are obviously passing through this. There's ice, which will obviously cool any gas that's coming in. And there's some liquid, but they haven't told us what that is. So that liquid might dissolve some of the gases, not all of them, because the delivery tube is not going into this, it's just there. So some of the gas coming in might dissolve. The rest of it will escape. And this will definitely go through lime water. And lime water, we know, is a test for carbon dioxide. So lime water should turn milky if carbon dioxide comes in. And any extra gas will be allowed to escape. These are safe gases, so we can allow them to escape into the atmosphere. First question. I'm just reading the last sentence. I don't need to go through the whole story. That's just wasting time. I'll first look at the last sentence to know what the question is. And then if I read the story, then it makes more sense to me. Describe a chemical test which can be used to show the liquid is water. मुझे कोई ज़रूरत नहीं है बाकी बातें पढ़ने की भी. Although I can read them, sure, no problem. But right now it's just telling me describe a test for water. I have two tests. One is you take anhydrous. That's very important word. Anhydrous cobalt chloride paper. Goes blue to pink. That is one test. The other test that we know is anhydrous copper 2 sulfate. Goes white to blue. Anhydrous is important. So test is to take any of these, and then the observation is the color change that I told you. Suggest why the boiling tube is placed in a beaker of ice. I'm getting water and carbon dioxide, right? So I'm assuming it's there to cool the water, because carbon dioxide can't be cooled with ice to become something else. It's only water that's going to form that liquid. So it is going to cool water vapor, because you don't want water vapor to go into the lime water. Carbon dioxide is also produced by burning the hydrocarbon. What effect does carbon dioxide have on lime water? It turns it milky. बहुत आसान है अभी तक तो. Okay, the experiment is repeated using, now we have values, 100 cm cube of 2 mole per dm cube sodium hydroxide. Okay, instead of lime water. Lime water also goes milky, which is an indication of carbon dioxide, but sodium hydroxide is also alkaline, which can react with carbon dioxide coming in. Because you know carbon dioxide is acidic. Carbon dioxide produced by burning the hydrocarbon reacts with sodium hydroxide in the conical flask. We know that. After the hydrocarbon has been burnt, the mixture in the conical flask is solution Q. Okay, solution Q is titrated with 1 mole per dm cube HCl. What is he doing? Let me explain. He had sodium hydroxide. That sodium hydroxide reacted with carbon dioxide. But how much reacted and how much was left over, we do not know. To know how much sodium hydroxide is left over, he is doing titration. अब इससे होगा क्या? He will figure out using titration how much sodium hydroxide was there. Using sodium hydroxide that was there, he will figure out how much actually reacted with carbon dioxide. क्यों? क्योंकि शुरू में initially he had 100 cm cube of 2 mole per dm cube sodium hydroxide. So the moles you can easily figure out, 100 over 1000 times 2. We can easily figure that one out. We know there is going to be what, 0.2 moles. But he's going to do titration again to figure out how much sodium hydroxide is left over. Because what if after he does titration, he figures out that sodium hydroxide is 0.7. Up 0.7 means that initially he had, 0.17, let's suppose. So 0.2 was the initial volume and carbon dioxide reacted with it. And when HCl reacted, HCl only found 0.17, which means the remaining, the 0.03 reacted with carbon dioxide. And that you can use to figure out how much carbon dioxide was produced. So he's a very smart guy solving these things. All right, initial and final readings of the 3 titrations are shown. Okay, A couple of things about titration: always write them to one decimal place, even if it is 0. Don't write 0. Don't write 0.0. Similarly, in the fourth row, we usually ask for the best titer or best titration results. Those are the two closest values. They're not the smallest value. They're always the two closest values. All right, so let's put them. Initial value is always the first one here. By the way, an important thing about burette. Burette does not measure the liquid that's inside. Burette measures the liquid that has gone out. So when you read the value, you always read it from the top. So you won't say this is 25.1, this is 24.9. All right, so initially 0.0, this is 24.9. That means 24.9 has gone out. This one, 5.2 is initial and 29.5 is the final. So you subtract them, so 0.3 and 24.3 has gone out. And this one is 14.3 as the initial and 38.8 as the final. So (24.5) has taken out. So the best two are the two closest ones, which is these two. Okay, so I take both of them. In the table, take the best titration result. I've done that. Use this best titration to result the average. One is 0.3, one is 0.5, the middle is 0.4, so 24.4. If you are not sure, just add the two and divide by, add the two values and divide by 2. So 24.3 plus 24.5, 48.4 divided by 2. Yeah, 24.4 again. Now this is the volume of HCl. That was the acid. And you already know the concentration is 1. Okay, calculate the number of moles of HCl in the average volume. You already know N equal to CV. So average volume is 24.4 over 1,000. And C is 1. So this is going to be 0.0244. You can also write 2.44 into 10 per minus 2. Both of them are acceptable. Okay, calculate the number of moles of sodium hydroxide in 25 cm cube of Q. Q, what was that? Q was the leftover sodium hydroxide. So mole ratio is the 1 to 1. So that tells me this is also going to be 0.0244. Calculate the number of moles of sodium hydroxide in 100 cm cube of Q. Now you can use ratio method. In 25, you had 0.0244. In 100, you'll have 4 times that, right? Because imagine if I divided all those 100 into 4 parts. So one of 25, the other of 25, another of 25, another of 25. All of them having this many same moles. So you add them all up, you multiply them by 4, basically. So 6, and this one is 7, and this one is 9. I'm just, let me calculate. Yeah, that's what I'm getting, 0.0976. Okay, so that's the number of moles I have in 100. Notice that the volume has changed. Calculate the number of moles in the original 100 of 2. So originally you had N equal to CV. Again, I always write the formula if I'm using the formula. If I'm using the formula, because it helps tell me that I'm putting the right values and I can easily revise it then. If you're using the formula, always write it. So this is going to be concentration. Now, this has nothing to do with the previous part. This is an unrelated part. And the examiner is trying to unnerve you over here because he's trying to confuse you a little bit, because now you'll be like, wait a minute, this has nothing to do with the previous part. You have to go back to the original values. So you are losing track of the calculations here, but that's fine. It's not so easy to confuse us. 100 over 1,000 times 2. So 0.2 is my answer. Okay. Use your answer to 4 and 5 to calculate the number of moles which reacted with carbon dioxide. See, I told you, this is the 0.0976 is what's left over, and 0.2 is what we started with. So 0.2 minus 0.0976. What I usually do is I assume that this is 0.2000 and this one is 0.0976. So I'm just subtracting 2,976. So that is 4 and there's the 1,000. So 0.1024 moles. You can use a calculator, of course. Use the equation. So this is the moles that reacted with carbon dioxide. Now, if I know sodium hydroxide, I know how much carbon dioxide reacted, because you see 1:2, that's the mole ratio. So 0.1024 would react with half of that. Now, if you study computer science, you already know the table that goes to 1024. Half of that is 512. So 0.0512. Okay, but again, calculate to the rescue. So yeah, and then mass of hydrocarbon burnt is this, M of hydrocarbon is this, calculate the number of moles of hydrocarbon burnt. Again, totally unrelated to the previous part, but that's fine. We know mass over MR, so number of moles is mass over MR. Again, I'm writing the formula, will not give me any marks, but it's still important for me to write it. So 0.73 over 86, whatever that is. Again, I'll use a calculator. So 0.00849. Now, while I've written this, I have not erased the value from my calculator. I will use this value if I need it in future. Okay, the general formula of alkanes is CnH2n plus 2. Use your answer to figure out N. Let's see. This is the moles, 0.00849, the moles of alkane. This is the moles of carbon dioxide. Now, we know from organic chemistry that whatever carbon is, however many carbon you have, that's the number of moles of number of carbon dioxide that you get. So for example, if I had CH4, I'll get carbon dioxide and 2 water. Why? Because usually the rule is C2H6, for example. The rule is you burn them, you get same number of carbon dioxide and half of that water. So 6 ka half 3, so 3 water, which tells me I'm going to get N carbons in 1 mole of alkane, which should equal to N carbon dioxide. So that is 0.0512 carbon dioxide divided by moles of the hydrocarbon, 0.00849. So this comes out to be a little above 6, so I'll just write 6. That's the number of carbons that I have. So this is C6H14. That's my hydrocarbon. Interesting question. Okay, I think this is the last question for today. A student does an electrolysis experiment to investigate how the length of time an electric current is passed through 1 mole per dm copper 2 sulfate affects the mass of cathode. Of course, this is copper 2 sulfate. We would expect copper to be plated onto the cathode. So the longer it takes, I'm expecting the greater the mass. The student passes a current of 2 amperes basically through the circuit for 5 minutes. So you have the time, you have the current. People who study physics know that you can put them together and get charge traveled. Removes the cathode. In fact, this is a technique that we can use to figure out Avogadro's number in a lab. Like, I'm sure this is the end of O levels, but if we had time, we could actually do this in a lab and figure out the exact value of Avogadro's number starting over here. This is a very simple method of doing this. Removes the cathode, dries it, and weighs it. So come back to this. So they're basically allowing copper to come to the cathode and then measuring how much mass the cathode has gained. Records the new mass. So, okay. So they do that for 5 minutes. In fact, 25 minutes. Wow. So they're getting more and more and more. Complete the table. So all you have to do is look at the changing things. So this increased by 19. So I'm guessing this would be an average of that. So what I'll do is I'll add 0.57 and 0.19 and divide them by 2. Okay, so 0.57 plus 0.19 divided by 2, that is 0.38. Do not assume that examiner has a range of answers that are acceptable. Just take the average. Similarly, 0.57 plus 0.95 divided by 2, that's 1.52 divided by 2, 0.76. So it's an exact number that you need. You don't need to give an estimate. Take a calculator, take the average. Okay. Describe the appearance of cathode when the current has been passed for 25 minutes. What's the appearance of copper? It's completely covered in copper, right? So it's going to be pink solid. It's important to mention both of those points because appearance is not just the color, it's also the state. Explain this observation. Why is this happening? Because copper is deposited on cathode. Okay. Student plots the graphs. Okay. Predict the increase in mass if current of 2 ampere is passed for 28 seconds. So what I can do is I can draw a straight line here. Okay. Wow, this is a straight line. And now I can figure out based on whether my line is correct or not. For example, over here, this is a little over 0, but of course you won't have the technology to zoom in an exam, but it's fine. But try to be as accurate as you can. Okay. Also, when you're drawing the line, make sure that the number of points above and the number of points below the line are exactly the same, or it's passing through all of them. For example, right now it's passing through all of them. So the value when it continues for 28 minutes, let's see. So 28 is over here, right? So I'll draw a line, and on your exam, make sure you also draw a line to show how you found it. It's not just enough to get the answer. It's also important to mention how you got the answer. So I'm going to guess I get this value, which is a little over 1.15. That's the one I'm getting. Okay. So is it 1.15? Let's see. No, it's 1.06 or 1.05, a value around that. So I'm getting 1.06. Now here's the thing. This is a 2-mark question. First of all, that's a hint for us to draw these lines. Secondly, let's suppose the examiner had 1.07 instead of 1.06. Then, because I've shown them that I drew the line is best fit, the number of points above and below the line are the same, and I've drawn the green line as well, this shows to the examiner that I know what I'm doing. And then it gives him very little leverage to take marks away. So that's why I will get 2 marks, even if my answer is 1.06 and their answer is 1.07. Student calculates the theoretical increase in mass of the cathode. He notices that the theoretical increase is greater than the actual increase. Of course, the theoretical increase is greater because what is he doing? He's literally just measuring copper that is deposited on an electrode. And how is he doing that? He's taking it, putting it on a balance, getting it back there. It's natural to lose some of the copper during that process. Maybe it just dropped into the solution when you took it out, or maybe it just was dropped while you were transporting it. So his method is not exactly very hi-fi. So it is possible that some of the copper dropped into the solution or did not separate from it. So yeah, so some copper was dropped into the solution. Okay. The experiment is repeated using copper electrodes instead of carbon. Okay, what happens on mass of anode? Anode will dissolve, right? Because anode will ionize. This is the first rule of electrolysis. A reactive anode ionizes. So it will decrease, the mass will decrease. The initial mass of copper anode is 4. Use the information to predict the mass of anode after 2 amperes has been passed through 1 mole for 15 minutes. So, okay. So for 15 minutes, how much mass has he gotten? So 15 minutes, the change in mass is 0.57. Okay. So 0.57, right? So this one, initial mass is 4. So he has lost 0.57. Again, 2 more questions, so show your steps. So this is going to be 3.43. So that's the mass that he has. You have to subtract it because the anode is losing mass. And yeah, that brings us to the end of today's paper. If you have any questions, feel free to send them in the group, the WhatsApp group, or to me on WhatsApp. I'll be happy to answer. All right. All the best. Keep practicing. I'll see you in class. Allah Hafiz.